Hey everyone, Krishna here, and I hope you all are doing great. So in this video, let's design another popular system design interview question, that is food delivery application like Swiggy or Zomato, and we'll just focus on core functionalities while designing the system. So if we talk about the functional requirements, the first is like user should able to search for food items or restaurants. That is the thing that we will consider. Then next is user should able to place the orders. Later, like restaurants should able to accept or reject the orders, and based on that, rider assignment should happen. So yes, these are a couple of functional requirements that we'll be focusing. Let me quickly note them down right over here. Yeah, so obviously the first is like searching the food items or restaurants, placing the order. Then restaurants should accept or reject the order, delivery partner assignment and all. These are a couple of functional requirements that we will be considering. And let's talk about non-functional requirements. Here, system should be highly available all the time, because most of the time users may just visit the application and look out for the food items. Okay, so it should be highly available rather than consistency. Next, the system should be scalable, as in we may have around 50 million users available on the platform, and during peak time, like during the lunch or dinner time, the orders may get placed. So obviously we have to consider those things as well. And there could be like 500K restaurants registered across from different areas. So yes, that is the scale that we will be considering right over here. The other things are like for payment processing and all, obviously consistency matters, but those things we are not covering right over here in this one. So yes, we can skip them. Let me just quickly note on the non-functional requirements as well. Okay, let's start designing the system now. The first is obviously we have these core entities before deep dive into the system. The entities will be like restaurants, owners, food items. Then there will be users, delivery partners. If we talk about the enums, like there will be status enum and all. These are a couple of things that we will be having. And talking about the APIs, mostly there will be REST APIs that we will be having. So while designing the system there itself, I'll try to add those APIs. Okay. So the first thing that we have to focus is like we have to ensure restaurant specific information is available in our system, so that users can start searching for the items or look out for the restaurants, and then they can place the order as well, right? So for that, restaurant generally communicate with the API gateway, and load balancing and all those things will be right over here. So the owners first they register themselves on the platform, and they can add the restaurant specific information. So these owners has to communicate with the system first. Next is like we have here restaurant service. These will be horizontally scaled, obviously, so multiple servers will be available. The load balancer communicates with this restaurant service, and then the job is from this restaurant service, whatever restaurant specific information we got, it will be put it into the DB so that it will get persisted. And we'll simply use relational database right over here. Restaurant DB is something what I can name it. And the data inside this restaurant DB is like restaurant ID, name, latitude, longitude for the location, the address, city, status, right? So these are a couple of things that are available, and then there will be like a list of menu items. This menu item will be separate table that we will be having, right? These are a couple of things we can hold inside this restaurant DB. Now, next is like we'll look out for this searching food items and restaurants, right? So clients or users started making requests to get the restaurant specific information, food items that they are looking out for in their nearest location, right? So again, the client has to communicate with the API gateway, load balancing and all. So yes, the same thing will be right over here. We have these users, and they started making requests to look out for the restaurants, nearest restaurants, and also they search something like pizza. So there will be a search service, and this particular service, it's just, yeah, search service. Let's see. So again, this will be horizontally scaled. The job is whatever user searches, based on that, it will pull out all the restaurant specific information that are available in that particular radius, and give it back to the users, and user can pick whatever restaurant they wanted to look out for, right? So this service can simply communicate with this restaurant DB to get the restaurant specific information, and give it back to the users. Okay, that's the flow that we have. But obviously, making queries directly to the restaurant DB will be really expensive, not a great choice, because we have to ensure that low latency is also we are supporting, and having so many queries, because generally most of the users keep on using the application to search for specific food items or restaurants and all, and these relational databases are not optimized for these type of tasks, right? So we have queries like select asterisk from the restaurant, where the food item equals there is this like command that we have, right? So we can use it, but obviously it does not support fuzzy searches or pattern matching, or even the typos that generally user make mistakes, right? So those things these DBs never supports, right? So we have to ensure that there is some system that is available which can be really fast and which can provide results as fast as possible, right? So for that we can rely heavily on Elasticsearch. Okay, so how this thing basically works, like let's talk about that. Okay, whenever any new restaurant specific information that comes into this restaurant's DB, or the owners updated the restaurant information or they deleted the information and all, what we generally do is these DBs generally commit the logs, and there are tools called DBZM and all. What they generally do is they monitor these logs. The moment they collect any new logs, the job is like they create an event and put it into the Kafka. Okay, so this process that we are following is we generally call it as a CDC pipeline. Okay, so change data capture is something what. So anything that is changing in the relational database that we have created, the result is something what we are capturing. The commit logs are something what we are keep on monitoring, and we are capturing them, and we are putting it into the Kafka, and from Kafka in a bulk there will be consumers who are keep on consuming these results. Okay, from the Kafka, the consumers keep on collecting these events, and these consumer workers, what they generally can do is like they will keep on in a bulk, they create a JSON like structure for these data that they have collected, and they can give it into the Elasticsearch. Okay, from Elasticsearch, how the data generally gets queried, so that these results that we are looking out is fast as enough, that we'll talk later. But now let's just add this particular flow right over here in this system. Okay, yeah, so as I discussed, there are tools called DBGM which keep on monitoring this DB related commit logs, and they'll put those events into the Kafka, and from the Kafka the workers keep on pulling those events, and they create JSON like structure for those DB related informations, like restaurant ID name, latitude, longitude, cuisine and all. And they in bulks they put these events in this particular document information into the Elasticsearch. Now this document specific information gets stored in Elasticsearch in source area, and it get tied with particular ID. So let us suppose this particular first restaurant's information get tied with doc1 ID, and there will be multiple such document IDs that are keep on getting tied and placed it into the source area. So the second job this Elasticsearch generally do is like it analyze the words which generally users searches for, right? Like the restaurant name or cuisines and all, and it tokenize them. So how things works is like if there is a pizza mania, that is the word that we have, and what these Elasticsearch first do is like it will tokenize them. So pizza will get separated, mania will get separated, and for this pizza, the document is, let us suppose that's the document we have where this pizza and menu is information available in the cuisine. So this pizza is tied with the document ID one. The menu is also tied with the document ID one, and this information is something what Elasticsearch maintains. Now instead of document basically tied with this pizza, here Elasticsearch uses inverted index. So this pizza basically tied with, I mean, these document IDs. Okay, this is how the data gets generally gets stored in Elasticsearch. Now whenever user searches for pizza, and obviously the query will be like users location and radius in which the restaurants who are available, and having these keywords, those information also filtering also we have to do. So in Elasticsearch how query works is like it will start looking out for pizza wherever it is available. Obviously there will be multiple sharded Elasticsearch data is available to which these queries generally goes, and it look out for the specific keyword that it is kind of looking out for, and these Elasticsearch obviously supports fuzzy searching or even typos that are available. So it will ensure that anything that is basically getting searched, we will be looking out for approximation information that is available. So even the typos and all, if there are mistakes, it will try to get the information correctly from these, and whatever the documents that are tied with this particular pizza, those documents are obviously stored somewhere in source area in the Elasticsearch. From there the data basically gets retrieved, and this way like the query will be really fast, right? Whatever we are searching, like we just have to look out for those words and get the documents, and based on rating, ranking and all, the information gets collected and feed it back to the user. So that's how the thing basically works via this one, and this way like will very fast, anything that is basically getting searched, it gets as quick as possible, and search queries generally works really smooth right over here. Okay, now let's talk about our next functional requirement, that is placing the orders. So we have order services right over here, which generally accept all the orders. Uh, so any incoming request from the client user side who want to place the orders, this order service will consider them, and it generally communicates with the payment service to ensure the payment happens, and then whatever order status that we have, it will get added into the order DB, right? So we have a database here, which is order DB. This is the order DB. And here inside this order DB, what data we collect is like order ID, user ID, restaurant ID, right? Status of this particular order. Initially, it is obviously in pending state. Then payment processor, whether it is going to be a cash on delivery or something like that. The pricing, every single thing. This order DB basically holds, and this is going to be again relational database. Once the data has been added into the order DB, this order service generally communicates with the restaurant's owners. For that, we have here restaurant service. So this will be restaurant order service. And this service generally communicates with, I mean, send a notification to the restaurants owners for the orders. And the job is like once owner accept or reject the order, based on that we have to update the order table, and then we have to update to the users as well. If restaurant owner accept the order, obviously we have to ensure that rider assignment is also we are considering into the account. And this particular flow, whatever we are doing it, right, like from the order to restaurant order service, directly communication, this works for a small scale system. But obviously if we talk about this particular scale, during the peak time and all, this communication does not work. So we have to ensure that we'll be again using event streaming flow right over here. So there in between this, we'll be placing Kafka here. So all the orders that are coming will go through Kafka, and that will ensure that during peak time the order service or restaurant order service will not get affected a lot. So here we have this order created, something like that, a topic we can have, which collects all the orders, and generally it sends these orders to the restaurant order service. And once owner accept the order or reject, based on that we can have another topic right over here. It could be like order status. So this particular topic, for this particular topic, we can have multiple consumers right over here. The first consumer would be like updating the order DB. So DB updation consumer is something like we can have worker which update the order. So yes, that's the first worker. I'll just name it as P1. Its job is to update the database. Whatever status that we got it right for that particular order, it will update it. Update, update the status. Okay. So yeah, that's the job for this particular workers. Then next workers are communicating directly with the user. So it is kind of a notification service. So it sends the notification to the user. And again, we can have another consumer which generally ensures that rider assignment is happening. Okay, so we can have consumer rider assigning service, something like that we can have. And that's like and how this works now. Let's ensure that rider is basically getting assigned to this particular user so that he can deliver the order. For that, again, like we have load balancer and all, where user registers them, riders or delivery partner registers themselves on the platform. And once they active in a particular location, they keep on sending their locations, and every 3 to 5 seconds they update their locations from their device, right? So these locations are so frequent that we cannot simply use database to hold these events. Obviously we have to use caching layer, in which these riders or delivery partners locations are keep on getting collected. And here we will be using geohashing. Okay, that is another beautiful concept that is available. So geohashing, generally what it does is like it divides the map into a grid and assign unique hash to each geographical area. In case if you want to understand that, I'll ensure to create another video and explain it properly right over there. So it create unique hashes for each geographical area. When any particular order is ready for pickup, we can identify the geohash of that restaurant and fetch a rider who is actually present in the same or nearby geohash regions. And once the riser assignment service receives all the riders information, obviously these data that we are tracing, right, for that riders, it is kind of obvious that the rider has to keep on updating their locations every 2 to 3 seconds. And we can generally collect all those locations, and we have to ensure that we are not simply adding it into the database. There should be caching there, because the data volume is tremendous, and simply putting it into the database and from there we have to fetch the information, it's obviously not possible for these type of systems. So we have to ensure that we are collecting the riders information in cache. Okay, and the data that I already told you is obviously Joe hash based information. That is how we are collecting it. Now once the rider assignment gets all the riders information, it generally sends the notification to all the eligible riders within that particular radius. The radius could be like 2 to 3 kilometers. In between that only, all the riders information we have collected. Now multiple riders may try to accept the order simultaneously. So obviously we have to ensure that distributed locking is something what we are using it. This concept is something I already covered it in previous videos, so you can go and watch that. And once a particular rider accepted the order, what we have to do is an event is something what we have to publish again from there, and that event get fired to users, to the restaurant owners, And obviously status is something what we have to update into the database as well. This particular rider has been updated and all. Okay, so once rider picks the particular order, user want to keep on tracing the location of that rider, right? We have to ensure that the rider is keep on firing his location, and user registers to that particular event in a form of like webhooks, or we can use server sent events again. So rider keep on sending the location in a form of events, and users keep on tracing that events. Okay, so let me just quickly add that flow. So the flow is pretty much straightforward now. Like once the order is been created, it update into the database, and then this order is basically put it in a form of event, and this from the Kafka restaurant order service consumes those, and send a notification to the owners. Owners once accept the orders, again we have another topic called as order status, which has multiple consumers who are consuming those events. The fun is like updating to the database. One can be update, send notification to the users, and then there will be a rider assignment consumer which consumes it, and look for all the nearest riders that are available from the cache, and it will send notification to all the riders. Riders once accept the orders for that particular delivery. We have to ensure that again we'll be having another Kafka topic through which the notification goes to the users, restaurants, and then once rider pick up the order, user wanted to check the location of the rider, so there will be an SSA event or webhooks to which it will keep on tracing the rider's location. Okay, so that's the general flow, I guess. If you understood this one, please make sure to like this video. Thank you for watching this one. Bye bye.